I want you to consider this kind of problem. Runways are numbered based on the direction they point. Don't know if you guys know this or not. Like the Tampa Bay runways, they point north-south. So if this runway was north, then its runway numbers would be 00 on this side, and I'm going to write it right side up so you can see it, but it would be written the other way so that you could read 18 if you were coming from the south. So a single runway has two sets of numbers, and those numbers are based on the direction that the plane is landing. So if you are landing on runway 00, they are expecting you to come in this way. And if you are landing on runway 18, they expect you to come in this way. It's 18 for 180 degrees and 00 for 0 degrees. Does that make sense? Now, interestingly enough, there are a bunch of runways that have had to be repainted in the last 10 years because their runway numbers have changed. Now think of it, this is kind of, I think, huge to me. If the runway number has to change, that means that the direction the runway faces has changed by 10 degrees or more, right? Because this is the 10th digit for 180. And it's changing because magnetic north is changing. The direction that the compass points is no longer the same as it was 10 years ago. And it's changing enough where it's changing by 10 degrees in less than 10 years. Now, it's in the fossil record that the magnetic field of the Earth reverses itself about every 50,000 years or so. But what's interesting is we don't know anything about the process. We're not really sure why the Earth has a magnetic field. We think it's because of the Chewy center and the fact that the magma and iron in the Earth is rotating at a different rate than the actual rate of spin of the rest of the Earth. And that's causing the magnetic field. But that really wouldn't explain why it's flipping. But we know it has flipped in the past. Truthfully, I don't want to be around when it does, but I really don't think there's anything that humans are going to be able to do to prevent it. And if you want to understand why I don't want to be around when it does, you should take a little look at something called the Van Allen belts. If you don't know what the Van Allen belts are, take a little dive into Wikipedia. It's an interesting read. You'll learn about Aurora Borealis and stuff like that. But you'll also understand what the Van Allen belts do for the Earth and why having a magnetic field would be nice. Mars doesn't have one. And look how that turned out. Now, I'm not saying this to be cryptic, but having a magnetic field is part of the reason we have an atmosphere. Without a magnetic field, we don't have Van Allen belts. Without Van Allen belts, the sun's rays can push the atmosphere off the Earth. We know that it also protects us from other stuff, but it's a good read. If you want a really interesting read, find the intersection between the Van Allen belts and Kennedy, the president. Because Kennedy would be the only president who detonated a nuclear bomb in the Van Allen belts before we signed a treaty with the former Soviet Union that we would not be detonating nukes in space. Arguably a good treaty to have. You've probably heard this sensationalized in movies, but detonating a nuke in space, although dangerous to things in space, causes an EMP on the ground, an electromagnetic pulse. It knocks out things like air traffic control, cell towers, radio communication. When he detonated it over the Pacific, all of a sudden all the planes flying in the Pacific couldn't see where they were going. Couldn't find the towers for the airports they were looking for. They had to all of a sudden start navigating by hand. So it's a thing. But the Van Allen belts, it's an interesting read. So here's the kind of problem I would like you to solve, and I'm going to go through how I want you to solve it. Let's say you want to land on a runway pointed due north. And let's also say, and this is just for fun, you would never land a plane with a 50 mile an hour cross breeze. A 50 meter per second cross breeze. 50 meter per second cross breeze would be about 110 miles an hour, so this is like hurricane strength wind. We wouldn't be doing it, but I'm using these numbers because they're simple to use. So let's say that the wind is blowing due east. Now here's the thing. Planes have a minimum speed they must maintain during landing. They go too fast and the wings work and lift the plane. They go too slow and they come down harder than they're supposed to and break the plane. They have a fixed landing speed. So let's say that your fixed landing speed is 150 meters per second. It's not. It would be much less than this. But about 150 to 200 miles an hour is about appropriate for the landing speed. Now here's the question. What direction do you point your plane in order to land on this runway? And we're going to watch videos of this, planes landing in a cross breeze. But what I'd like you to see is how you do this problem. It's not much different than the problem we've done. But this is what I'd really like you to be able to do. This is steering your vector. Right? We're trying to steer the plane. And we're trying to do so in such a way that our result is in a particular direction. All right? So, I want to show you how to do this. And this particular one is not hard. There's a bunch of you in the room who could do this because you can already see that there's a right triangle here. So all of you who are running off and doing it, because that's the kind of people you are, I want you to realize the reason I'm going to teach a procedure is for when I decide to change it up and have the wind at an angle to the runway, or better yet, change the whole thing and have the runway at an angle too. Now this problem is actually pretty hard. It's very tedious. When the runway is no longer lined up with a Cartesian coordinate, you got things you got to do. This problem is the same level of difficulty as this problem if you learn the procedure. So we're going to do this problem. I'm going to talk to you about a procedure. The procedure is almost identical to what you've already done. Almost identical, with one minor exception. So let's take a look at this problem, okay? First, you will have to kind of use your imagination and decide what direction the plane would probably be likely to fly. So can I get like everybody's approval that you're probably not going to point your plane this way in order to land like this? And that it would make no sense to point your plane like down here or down here if you wish to go down the runway in the north direction. So I think I've got everybody on board that you're probably going to aim this way. Good, because if you can't do that part, there's no point in going forward. So here's how I want you to start. We have two vectors still. We're going to have a vector for the wind and a vector for the plane. The only difference is that we don't know the direction of the plane. So let's treat the problem the way we've been doing them already. The wind's easy. A quick picture of the wind shows me that it is along a cardinal direction, so converting it into rectangular is pretty easy. Wind. I have my x and my y. The wind is going to be 50 in the x direction and 0 in the y direction. The plane, on the other hand, I don't know what direction it has to go. I just know the size of its velocity. I'm not going to change the procedure. In fact, I'm going to convert, bless you, I'm going to convert its velocity from polar into rectangular. Except I don't have an angle. But I know it's going to be some angle. And I know this side is going to be 150. Right? I don't know what that angle is. But I know it's got to be that big. So, good so far? All right, so procedure is the same. I'm going to wrap a triangle around my angle and enclose the triangle. So there, I've wrapped a triangle around the angle, enclosing the triangle, creating my right angle. I'm going to label my opposite side and my adjacent side. All of this is still the same. Here's the difference. When I do sine of theta equals opposite over hypotenuse, I'm not going to get a numerical answer. I'm going to get an expression. I'm going to multiply both sides by 150, and I'll get opposite equals 150 sine theta. Same for the cosine. So cosine theta is adjacent over 150. So my adjacent is going to be 150 times the cosine of theta. Everybody following so far? Now, that means that the plane is still going to have an x component and a y component for its velocity. The x component is going to be the opposite, because that's the direction it points, and it's negative. So negative 150 sine theta in the x direction. The y direction is going to be the adjacent side. So that's upwards, positive 150 cosine theta in the y direction. So I've still converted it, but now, I don't have numbers there. But here's where you have to kind of make a leap of logic. I still have to add these together, but I know something about the result. I know the result has to be due north. The only way it can be due north is if the sum of the x components equals 0. That's the only way I can land due north. Now, I don't know what theta is, but 50 minus 150 sine theta has to be equal to 0. Right? That's the only way the x components add to 0. But now I know everything, right? We can work out what theta is. We can do the calculus. It's not even really calculus so much. It's just solving for an unknown variable. So work out. We'll get that theta equals the inverse sine of 50 over 150, which I'm pretty sure is 19 degrees. So the answer to my problem is fly my plane 19 degrees west of north. That tells me the actual direction to face the plane. Now more than that, this sum, which is 150 cosine 19 degrees, this is still the result of the plane. That's still going to be the ground speed. Meaning it's how fast the plane is going to travel along the runway as it's landing. The problem is that the plane is going to be facing this way while it's landing. Now, anybody who's been on an airplane has probably had to land sometime when it's been windy. Generally it happens. What's interesting is that that's what planes have to do. They have to figure out a way to be moving down the runway, facing off the runway, and then when they actually touch down and put the wheels down, they need to move the front of the plane over so now it's facing down the runway. It's not uncommon. But before I go on and we watch some videos of that, does everybody follow that progression pretty well? Now, you'll notice two things, I hope. I'm sorry, did you have your hand up? Okay. You'll notice two things. One, there's minor changes to what we had to do. The first change is you do have to anticipate the direction of the plane. You have to pick an angle that you're going to use and give it the reference so your sine and cosine for your unknown angle work out in the right place. The next thing is you have to zero out one of your components. Meaning you have to figure out ahead of time which one of those is going to have to be 0. The only thing that would have been different if the wind was at a different angle was I would have had a number here and here. They wouldn't be 0. That's the only change. Now, if you're able to do this, I want you to prove it. I'm going to post 2 pieces of practice that are just like this, but where the wind will not be in a cardinal direction. If this is beneath you, and some of you have that look on your face like it is, then you attempt the 3rd question. Because in the 3rd question, I'm going to have the runway at an angle as well. And for those of you who need to do the 3rd one, because that's who you are, start there. And understand that if you want to do that, you have to turn your runway into your cardinal direction. I mean, the only way for you to solve a question like this is to make the runway 0 degrees. That means all your other angles have to be adjusted to do it. So I think I've got 3 people in the room, 3 groups of people. I have people who are still struggling with the calc, the little stuff. You guys, do the practice that's already been posted. I think this room is predominantly people who can do this problem. Walking around the room, I did not see hardly any trouble with calculus. I'm sorry, with trig. I meant trig. You guys do questions 1 and 2 on the practice tonight. And then I have a small group of people who this is nothing to them. You should try question number 3. Does everybody understand? If you can do question 1 and 2, you're working at the level I need you to work at so we can be done with this. So I would like to be done with this.